Section 4.3, Calculus 1, how derivatives affect the shape of a graph. So first fact, if f prime of x is greater than 0 on an interval, then that means that f of x, our original function, is increasing on that interval. And here we have a graph of some arbitrary function. And notice wherever the derivative is positive, meaning graphically the slopes of our tangent lines would be positive, right? All of the tangent lines here, as well as over here, they're illustrated with the highlighted line. Anywhere that the slope of the tangent line is positive, we can tell that our function is increasing from left to right. Similarly, if f prime of x is less than 0 on an interval, then that means our function f of x is decreasing on that interval. And you can see here illustrated below that these tangent lines drawn to the curve would have negative slopes, meaning f prime of x at these tangent lines would be negative. And on this interval that's highlighted here, the function is decreasing. So this is a fact that we're going to use now in order to identify our local extrema or local mins and maxes for our functions. So here is the first derivative test. If f prime of x changes from positive to negative at c, then f of x has a local maximum at c. And notice this is illustrated below. F prime of x changes from positive to negative. So if you have a positive derivative, that means the function is increasing, right? The slope of the tangent line would be positive. And then it switches to negative. Well, exactly where that switch happened is where we have a local max. And similarly, if f prime of x changes from negative to positive at c, then f of x has a local minimum at c. And here the local minimum is illustrated below. So the derivative went from being negative, slopes of tangent lines were negative, to positive. So the function went from decreasing to increasing, and where it switched from decreasing to increasing, we have a local min. Now notice both of these, the local max and the local min, are critical numbers, since the derivative, f prime of x, is equal to 0 in this case, or it could also not exist. All right, save this first derivative test, and we're going to apply it for some of the examples later in the section. Now moving on to concavity. If the graph of f of x lies above all its tangent lines on an interval I, then f of x is concave up on the interval. And what this means when we're speaking in terms of derivatives is that the second derivative for all the x values on that interval would be positive. Well, what does something that's concave up look like? If you notice, graph down here below, this portion of our function is concave up. It resembles a parabola opening upwards, if you want to think of it that way. And notice here, the graph of the function lies above all of its tangent lines. So if we draw tangent lines to this function, right, everywhere I draw a tangent line, those lines are below the graph. So that's how we base our definition for concave up, that the function lies above all of its tangent lines. Similarly, if the graph of f of x lies below all of its tangent lines on an interval, then f of x is concave down on that interval. And notice here, this portion of our function in blue is concave down. See how the function lies below all of the purple lines, all of the tangent lines, and any more that you would draw. And what this means when we're looking at its derivative is that the second derivative, f double prime of x, is less than 0. Now, where the graph switches from being concave up to concave down, or vice versa, is called an inflection point. Okay, so a point P on f of x is called an inflection point in f of x if f of x is continuous at P and f of x changes in concavity. Okay, so there has to be a change in concavity in order for a point to be considered an inflection point. And just a little something to help you remember which way it looks like: concave up like a cup and concave down like a frown. All right. Last little tidbit is the second derivative test. The second derivative test is applying the second derivative to identify where we have local mins and maxes on our graph. So f of x has a local minimum at c if f prime of c equals 0 and the second derivative is positive. Now remember, if the second derivative is positive, that means the graph is concave up. So it would look something like this. And also, we know that f prime of c is equal to 0. So f prime of c would equal 0 here. Say that's c. Here's c. F prime of c equals 0. And clearly, this is a local min. And we can also use the second derivative test to identify local maxes. So f of x has a local max at c if f prime of c equals 0. So we have a horizontal tangent. And f double prime of c is less than 0. So that means it's concave down, like a frown. Oops. And here would be c, where f prime of c is 0. There's c, and clearly this is a local max. Typically for this section, the first derivative test is usually more useful to identify local mins and maxes, but when we get to later section on optimization, the second derivative test can be quite nice. If f double prime of c is 0, the second derivative test gives you no information, so you have to actually go back and use the first derivative test to determine whether you have a local min or max or nothing at all. All right, so let's look at an example. Find the intervals of increasing, decreasing. Find the local min and maxes. Find the intervals of concavity, and find the inflection points. Before we proceed, it's really important to identify the domain of your function because you can't have a min or a max or an inflection point or anything like that at values that are outside of the domain. So if we notice here, f of x is a rational function, but there are no restrictions because the denominator is never going to be 0. So the domain for f of x is all real numbers. That'll make things a little bit easier. Okay, so to start off, we're going to find the intervals of increase and decrease. In order to do that, let's first find f prime of x. So f prime of x is equal to, I'm going to need to use the quotient rule. So I have low d high, x squared plus 3 times derivative of the numerator 2x minus high d low, x squared times derivative of the denominator, which is 2x over the denominator squared, x squared plus 3 quantity squared. All right, now from here, let's distribute and clean up the numerator, simplifying and combining like terms. So this is going to give us 2x cubed plus 6x minus 2x cubed over x squared plus 3 quantity squared. And then I'm just going to be left with 6x over x squared plus 3 squared. So here's my first derivative. Now, I want to identify all the critical values. So let's find the critical values. They come from two places, remember, where f prime of x is equal to 0 and where f prime of x does not exist. Always list out and explore both cases. So if f prime of x were to equal 0, remember, all you need to do is focus on when the numerator is 0, because the denominator being 0 would just make the expression undefined. So that would mean 6x would equal 0. So x equals 0 is a critical value. F prime of x does not exist would mean that x squared plus 3 squared is 0, so x squared plus 3 would be 0, but that's not possible. That would mean x squared has to be negative 3, so there's none from this case. No real numbers, don't worry. We're only dealing with real numbers in our calculus career for right now. Okay, so what we want to do is test now and see if x equals 0, this critical value is perhaps a local min or a max. And the way you want to do that is by making a number line. So you make a number line. And when we're applying the first derivative test, this is a number line testing the sign of f prime of x. Okay, you're going to list your critical value or your critical number on the number line. And then we're going to substitute values on either side on the two intervals into the derivative, into whatever we labeled our number line, in this case f prime of x, to see whether it's positive or negative. So if I plug in something smaller than 0, say x equals -1, into the derivative. So if I plug in x equals -1 into the derivative, remember here's my derivative. Well, the denominator's always positive. And if I plug in -1 into the numerator, 6 times -1, that's going to be -6. So the derivative is going to be negative on the interval from -infinity to 0. Well, what does that mean for f of x? That means f of x is decreasing. Very good. Now let's plug in something on the other side of 0. Anything from 0 to infinity would do. How about x equals 1? So going back to the derivative here, if I plug in 1 into the numerator, that's going to be +6. The denominator is always positive, so this is going to give me a positive number, which means my function is increasing. So this describes the behavior of f of x. Well, look at the graph. Look at what's happening. If my function f of x goes from decreasing to increasing, what does that mean happened at 0? Well, we have a local min. So we have a local min f of 0. And let's go back to our original function and see what would f of 0 be. So I'm going to substitute in 0 for x here. So I'm just going to have 0 over 3, which is 0. Do I have a local max? No, in this case, I do not. So state it. That way it shows that you considered the case, not that you were careless. All right, and then we're going to list the intervals of increase and decrease. So the function is increasing on the interval from 0 to infinity. You never include the critical values or the mins and maxes when you're listing intervals of increase and decrease. Those are turning points, right? Technically, the function is not increasing or decreasing there. And then the function is decreasing from -infinity to 0. All right, so that's the answer for part A and B, increasing, decreasing, and mins and maxes. Okay, so that's parts A and B. Now, part C and D ask for the intervals of concavity and the inflection points. In order to find that, I need my second derivative. So I'll just write out again that f prime of x was equal to 6x over x squared plus 3 squared. So now let's go ahead and take another derivative. So f double prime of x is going to be the denominator, x squared plus 3 squared, times derivative of the numerator, which is 6, minus the numerator, so 6x, times the derivative of the denominator. So I'm going to need to use the chain rule. I'm going to have times 2 times x squared plus 3, which is now to the first, and then times the derivative of x squared plus 3, which is 2x. Over, in the denominator, I'm going to have x squared plus 3 squared squared, so x squared plus 3 to the 4th. All right? Now here's where a lot of students struggle to simplify their second derivative. Before you start getting all gung-ho and multiplying everything out, you want to factor out the GCF, the greatest common factor, to save yourself lots of heartache. So what do these two terms in the numerator have in common? Well, I can take out an x squared plus 3 from both, right? And I can also take out a 6. That's it. But that will do me a lot of help. So I'm going to take out a 6 and an x squared plus 3. And then let's see what's left over from each of the terms. So from this first term here, if I take out a 6 and an x squared plus 3, I'm left with just x squared plus 3 to the first. So I don't need any parentheses on it. Minus, and then now I've taken out from the second term the 6 and the x squared plus 3. So what's left over? Well, I have 2x and another 2x. So that's the quantity, 2x squared or 4x squared. Over the denominator, which is still x squared plus 3 to the 4th. All right. Now let's start simplifying, and notice I don't have to do a bunch of foiling and multiplying and combining like terms. I'm already in a pretty good place. So first thing I notice is x squared plus 3 in the numerator cancels with one of the x squared plus 3's in the denominator, so now it's only going to be cubed. And then I still have here 6 times the quantity, 3 minus 3x squared over x squared plus 3 cubed. And remember, we're going to find the zeros of the second derivative in the numerator and the denominator. So you want it as factored and simple as possible when you're, in order to know how far to simplify your derivative so that you can find those zeros easily. Meaning, I want to take out this 3, right? And now I have 6 times 3, so 18 times 1 minus x squared over x squared plus 3 cubed. Okay? Lovely. So here's my second derivative, and then now this is going to help me identify the intervals of concavity and potential inflection points. Okay, so for potential inflection points, we find them similar to the process that we use when we find critical values. So they come from where f double prime of x equals 0, or where f double prime of x does not exist. So if f double prime of x equals 0, that means the numerator equals 0. 18 is never going to be 0, so it means 1 minus x squared would be 0, which means x would equal plus or minus 1. If f double prime doesn't exist, that would mean the denominator is 0. But remember, the denominator is x squared plus 3 cubed, so x squared plus 3 would equal 0, and we already said that this doesn't have any real solutions. So my only possible or potential inflection points are at positive and negative 1. All right, we're going to proceed similar to how we conducted the first derivative test. So I'm going to make a number line, list my potential inflection points, which are negative 1 and positive 1. And then I'm going to label the number line f double prime of x. So that's where I'm going to be substituting in the values when I'm testing my intervals into the second derivative. Always make sure you label your number line so you don't get confused where you're substituting things. All right, so let's go ahead, pick a value in between negative infinity and negative 1. How about negative 2? So I know, again, the denominator is always going to be positive, because when I square a number, it's positive. If I add 3, it's still positive. And then if I cube it, things aren't changing. So really, I only need to pay attention to the numerator. If I plug in something like negative 2 and square it, it's going to be larger than 1. So the numerator is going to be negative. So if I substitute in x equals negative 2, the numerator is negative. What does this mean? Well, it means f of x is concave down, since the second derivative is negative. So this is what f of x is doing. All right, between negative 1 and 1, what's a nice number to plug in? I vote for 0. Again, I'm substituting this into the second derivative. So 18 times 1 minus 0, that's going to be positive, which means f of x is concave up. Lastly, the interval from 1 to infinity. We can try something like positive 2, and 1 minus 4, that's going to be negative. So f of x is concave down on that interval. All right, so we can list our intervals of concavity. So the function is concave down from negative infinity to negative 1, union 1 to infinity. They have to be in order from left to right. And then the function is concave up from negative 1 to 1. And what does this mean? That I have 2 inflection points, right? There was a change in concavity. So I have inflection points, f of negative 1 and f of positive 1. And we want to also give what the function value is at those points. In case you forgot, I'll remind you, f of x is x squared over x squared plus 3. So if I plug in 1 or substitute 1 into the function, I'll have 1 over 1 plus 3. So that's 1/4, and the same thing for negative 1. So these are both 1/4. All right, very nice. That concludes that example. that's not quite the shape I was going for. Hold on. Now, let's do one more with perhaps a more complicated derivative and some domain restrictions, just to spice things up and show you what's out there. Okay, so we'll go through the same process. We're going to find the intervals of increase, decrease, local mins and maxes, intervals of concavity, and inflection points. So next example, little bonus problem. In this case, our function f of x is x times the square root of x plus 1. Now be careful here. I have a domain restriction. Remember, for radical functions, the argument cannot be negative, which means x plus 1 has to be greater than or equal to 0, so x has to be greater than or equal to negative 1. So my domain is the interval from negative 1 to infinity. Always write that out first because it will affect your answers. All right, great. Now let's go ahead and find the derivative. So f prime of x is going to equal, now I need to use the product rule here. So I'm going to leave x alone and then take the derivative of the square root of x plus 1. So that's going to be 1/2 x plus 1 to the negative 1/2 plus derivative of x is 1 times x plus 1 to the 1/2. Leave it alone. Okay, now I'm going to rewrite everything using radicals. So I'm going to have x over 2 rad x plus 1 plus, and then this is rad x plus 1. Now I want to get a common denominator. So the common denominator is 2 rad x plus 1. So I need to multiply this second term by 2 rad x plus 1 over 2 rad x plus 1. And then now I'm going to be left with x over 2 rad x plus 1 plus, now notice, if I have rad x plus 1 times rad x plus 1, that's just going to be x plus 1. So I have 2 times x plus 1 over 2 rad x plus 1. And then I can go ahead, distribute, and combine like terms in the numerator. So I have 2x plus 2 plus another x, which is going to leave me with 3x plus 2 over 2 rad x plus 1. So there's our first derivative, and now we're ready to roll. Okay, let's find our critical values. So remember, critical values come from two places. First place to consider is when f prime of x is equal to 0. So that would mean the numerator, 3x plus 2, is equal to 0. Solving for x, I get x equals negative 2/3. And that's within my domain. Remember, my domain is from negative 1 to infinity. So this we can consider. Now what about where f prime of x does not exist? Well, f prime of x does not exist if the denominator is negative 1. But that's an endpoint. That's not within, there's no open interval around negative 1. It's an endpoint on my domain. So since this is an endpoint, it cannot be a local min or max. Okay, if you need a review on that, you can check the video on section 4.1 that discusses that in more detail. All right, so actually I only have one critical value to consider. So that's not a critical value at negative 1, only negative 2/3 is a critical value. Whoop. Now let's make our number line. Be careful, no arrow on the left-hand side because my domain is only from negative 1 to positive infinity. So there's negative 1, this is f prime of x, and I'm gonna list my one and only critical value right here at negative 2/3. Okay, so I'm gonna substitute in values into the derivative. Notice again, like last time, this is actually pretty convenient. The denominator, this is always going to be positive, right? If I have a radical and then I multiply by 2, that's going to be positive. So say I plug in something between negative 1 and negative 2/3, like negative 0.8 or something, then the numerator is going to be negative, which means my function is decreasing. And then if I plug in something larger than negative 2/3, like 0 or 1 or anything else, then the derivative is going to be positive, which means the function is increasing. So we can list our intervals of increase and decrease. The function is increasing from negative 2/3 to positive infinity, and it's decreasing from, be careful, -1, not including -1, to negative 2/3. These are always open intervals. Do I have any local extrema? Well, it looks like here I have a local min, right? Look at what the function's doing. It's decreasing and then increasing. So we have a local min at f of negative 2/3. I'm going to substitute that into my function. Remember, f of x is x, so negative 2/3 times rad x plus 1, which is going to be rad 1/3. So this is approximately negative 0.4. Do I have any local maxes? In this case, no. But list it out so that your teacher knows you thought about it. Okay? Good. So we took care of increasing, decreasing, local min or max, and we've used the first derivative to completion. Now it's time to look at the second derivative. All right, here we go. Just as a reminder, f prime of x, I'll rewrite it here, was 3x plus 2 over 2 rad x plus 1. So f double prime of x, using the quotient rule, I'm going to have 2 rad x plus 1 times the derivative of the numerator, which is 3, minus the numerator, 3x plus 2, times the derivative of the denominator. So I'm going to have 2 times 1/2 times x plus 1 to the negative 1/2 all over the denominator squared. So that's going to be 4 times x plus 1. All right, very nice. How to begin simplifying? Well, as soon as I notice I have a negative exponent, technically I have a complex fraction, right? Because that negative exponent, I would rewrite that quantity in the denominator with a positive exponent. So what you want to do is just multiply the numerator and denominator by x plus 1 to the 1/2, so I can clear out that complex fraction. Okay, and then now some really nice stuff's going to happen. Have no fear. So when I distribute x plus 1 to the 1/2 to the first term, notice I have another rad x plus 1. And that's pretty cool because rad x plus 1 times another rad x plus 1 is just going to give me x plus 1. And then what else is going on? I have 2 times 3, which is 6. So this is 6 times the quantity x plus 1. Don't forget your parentheses. So far, so good. Minus, and then let's see what else is going on in the numerator. We actually have a bit of a cancel party. So 2 and 1/2 cancel. And then now x plus 1 to the negative 1/2 is going to cancel with x plus 1 to the positive 1/2. So all I'm left with is 3x plus 2. Just don't forget your parentheses. So the numerator is looking a lot better already. Denominator, I'm just going to rewrite it as 4 times the quantity x plus 1 to the 3/2 now. And then if I distribute, this is 6x plus 6 minus 3x minus 2. So I'm just going to be left with a positive 3x plus 4 over 4 times x plus 1 to the 3/2. And there's our second derivative, all cleaned up and snazzy. Woo, come on. There we go. All right, now let's find our possible inflection points. So similar to critical values, they come from where f double prime of x equals 0 or where f double prime of x does not exist. Okay, so if f double prime of x is equal to 0, that would mean the numerator is equal to 0, which means x would equal negative 4/3. But negative 4/3 is smaller than negative 1. And remember, my domain is only from negative 1 to infinity. So this is not an element of our domain. So it's not a possible inflection point. It wouldn't even make it on the number line. We're not considering it. Similar to f double prime of x not existing, notice that would mean 4 times x plus 1 to the 3/2 equals 0, but that would mean x equals -1, and that's outside. That's the end point. So that's not a contender. So we're not going to consider that one either. Oh no, what do? Just proceed as usual. It's actually going to be even easier than last time, okay? So no possible inflection points. That means the concavity is consistent throughout the whole graph. So we just got to determine what kind of concavity we're talking about. So make your number line, but just be careful. The domain's only from -1 to infinity, so don't put arrows on both sides. -1, this is my number line for f double prime. And look at my second derivative. You actually don't even need to plug anything in. The denominator's always going to be positive. Right? If I raise something to the 3/2 power, and my domain's only from -1 to infinity, then that's going to be positive. Now the numerator, keep in mind you're only plugging in x's from -1 to infinity, so the smallest the numerator is ever going to be is 1, so it's always positive. That means my second derivative is positive, so my graph is concave up, always. But don't write always for your answer, right? The graph is concave up only where it actually exists, meaning on its domain. So it's going to be concave up from -1, but not including -1 because the second derivative doesn't exist there, all the way to infinity. It's not concave down anywhere. Just list it so we know you thought about it. And there's no inflection points. Okay. If you're curious, I recommend trying to sketch this by hand, putting all the information together. We're going to actually do it later on in the chapter, or you can just type it into some online graphing tool just to get an idea of what the graph looks like. I think you might find it interesting. So that concludes section 4.3. Don't forget to comment, like, and subscribe.